Okay, so let me summarize what we talked about last time. So our interest is basically to calculate the invariant polynomials, and as I told you that invariant polynomial is nothing but the Lagrangian that we are dealing with, and those operators are basically my invariant polynomial. So that is the first target, and the second target would be how to convert those polynomial form into a covariant form, which is quite known to you guys, right, in the like d mu and all those things. And the prescription that we are talking about, that basically based on the symmetries and also the what kind of fields you have. And for our construction, we are not considering gauge fields, rather we are considering a set of phi, psi, which is the fermion, then f mu nu, and then the covariant derivative. Why covariant derivative? Because by construction we want to construct the operators which are basically gauge invariant. Okay, and also the gauge fields are basically hidden within this f mu nu and d mu. So these are my basically the variables. Okay, and while talking about the symmetries, we have these internal symmetries. Okay, and we have these space-time symmetries. Among the internal symmetries, we are interested in which one? Which are basically compact and connected group. And for example, SUN, SO2N, SO2N plus 1, and symplectic group. And all are basically compact groups, and we are learning how to calculate the characters for them. But let me make a passing comment. What I mentioned, that we need a special attention for the space-time symmetries, because space-time symmetry is non-compact, and as we are working in a 3 plus 1 dimension, so we'll focus on this SO3, 1. So the formalism, what I am discussing now, is specific to the compact connected group, and more specifically for the SUN, because as I mentioned last time, our primary target is basically to construct the SMAP operators, what team is talking about. Okay, but certainly we can generalize this prescription for other groups and for other space-time dimensions. Right. So now to do that, what we have understood that there are some representations for each such groups are there, and we say there is some kind of a character function we'll be able to write down. Right, so there is a one-to-one mapping between these different kind of representations and the character of that thing. And what are these characters? They are basically function of the torus coordinate. So these are my maximal torus coordinates. Right. So now, if I demand that there is a character function I can calculate for each representations, then I would expect the kind of property you would expect from this representation that should be reflected in the characters. So in between, we'll try to cross-check and cross-validate this statement. For example, if I take two representations, for example, SU2 2-dimensional and let's say 3-dimensional, right? So these two representations are independent from each other, right? So now, if I write down a character function which is like polynomial in this torus coordinates, okay, then I can calculate another polynomial corresponding to these 3-dimensional representations. So what would I expect? That they are orthogonal, right? So this is the property, that's why the character satisfied. They are orthonormal. Okay, and that you can see the consistency of the independence of the different representation of this group. Okay, so when you calculate the characters, you can explicitly check. Okay, you take any characters, characters of any representations which are basically same, then you should get 1. Okay, if you take character polynomial of two different representations, you should get 0. Okay, so that is one way to cross check that your calculation of the characters is consistent with the representations. Because this side we are a bit familiar that how to deal with the groups and the representations. Okay, this is a kind of a new language. So what we can do, we can always cross validate by our old information. Fine. Now the second part that we talk about, which is statistics, which we define as exponential of some r equal to 0 to infinity. Okay, and then we talk about some r and then phi r, right? And this we didn't propose initially. What we did actually, we actually, phenomenologically way we derived this quantity starting from a E1 symmetry of a complex scalar field, and then we construct what are the my invariants, and from there we map this idea, and then we try to define some quantity which is more like a generating functions. Okay, and this is not restricted to any U1, rather we propose that for any connected compact group we can construct this kind of statistics. That's the generalizations. So now if you look at this quantity, okay, sorry, there will be some, yeah. So if you look at this quantity, what is this exponential series? Okay, the exponential series tells you, like, you just take r equal to 0, 1, 2, 3 and all those things is a product of the characters, right? So you can see the one term will be like chi r times chi r, and then you have a chi r, chi r, chi r, and so on, right? That's how we will expand this series. Now this is the actually very similar what we have this for these representations, because for any, for example, let's say SU2, I start with the lowest dimensional fundamental representations 2, right? And now what I can do, I can repeatedly use these representations and I can construct all other higher dimensional representations, right? For example, 2 cross 2, from there I can get adjoint representation 3, then 2 cross 2 cross 2, from there I can construct the more higher dimension 4, and so on. So I can construct this, chi r, which is basically corresponding to some kind of representations. By the repeated action of this chi r, I am constructing a polynomial which contains all the informations, and this is infinite series, so it's capturing all the informations about the possible representations that you can have. Okay? Yeah, this part is slightly tricky, so yeah, I am stopping this time and you have a question. Okay, so that's what I'm saying, that instead of a mathematically providing a definition of a invariant series, what we did actually, we started with a very simple scenario where I have a E1 symmetry, right? And then first I construct the invariants. Okay, so if you remember that invariance was 1 minus phi star phi inverse, right? And then this quantity I can write down in integral form. Okay, and that was basically my, if you remember, 2 pi I dz by z mod z equal to 1. Okay, and then we have this statistics kind of thing, exponential this quantity, right? So I'm writing the PE. So then, but this is E1 symmetry like a abelian, right? And the idea is basically if you have a one abelian thing, now you can think of a geometry which is like a maximal torus, which contains basically E1 times E1 times E1 times all, right? So now, for connected compact group, I can always define a kind of maximal torus corresponding to that, which is a product of this abelian subgroups, right? So now if I can do for one E1, and that guides me, I can do repeatedly that thing for multiple E1s as a product. And that's how I can use the non-abelian groups in terms of a torus coordinates. I can write down the character. So that's the idea. Okay. Any other question? Yes, so in principle that should be done actually, but I mean there is some glitch, I will say what is the thing, but what the message actually, that why this exponential series carries information about all the representations. Because the infinite series is a product of all the fundamental representations of infinite times. So you cannot generate any other representation which doesn't belong to this. Just to convince you that this exponential argument, when you expand, okay, you will not be left with any representation which belongs to that particular group. Yes, everything. But this is for the scalar. For the spinorial, I'll define how to do that thing. But the idea is basically same. Yes. Loud. Yeah. Yes. 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 But the thing is basically, as Obik was asking, that then is it enough to just know the character function for a lowest dimensional fundamental representations? The answer is no. Because thing is, once you go for higher and higher, for example, you calculate 2 cross 2 cross 2, 5 copies, right? So then it will contain many representations, right? So then you do not know which part belongs to where. You can have a symmetric component 3 terms, not symmetric components some other terms, right? So that's why this ensures it will be captured all the informations, but what is the exactly character functions of individual representations, that we have to calculate. And that the technique, yesterday what I give the formula, that we learn. But this is the discussion is basically to make sure that this is the quantity which captures the information about all the representations of that group. Because all the representations are actually you can derive by starting from the lowest dimensional fundamental representations. Okay, so when I'm saying fundamental, loosely speaking, yeah, fundamental, anti-fundamental both. Okay. So that's why this quantity is enough to take care all the representations for that given group. Fine? Okay. So now, so then we have for the SUN case, we have defined the characters of some irreducible representations, okay, and we defined as epsilon R1 to epsilon Rn minus 1, and then we have epsilon n minus 1 epsilon 1, right? And we have seen, I am not explicitly writing this determinant because that we have already seen how to expand this determinant. And we have argued actually that this quantity, okay, is representation independent. Why? Because these are my torus coordinates, okay, and we know that there is some redundancy because there are some n number of these torus coordinates are there, but for SUN rank is n minus 1. So I would have n minus 1 number of independent torus coordinates, which I define as a Zi. So they are basically function of some Zi. Okay, and we have seen that starting from a highest weight state of a lowest dimensional fundamental representation for SUN, which is basically we have written down as a 1 0 0, right? And then we looked at the Dynkin diagram for this SUN, which is n minus 1 number of block, and immediately I can write down the Cartan matrix. So just put this block, n minus 1 by 2 times, okay, and then basically this first row you define as alpha 1, second row alpha 2, and so on, and you can construct the weight tree by subtracting alpha 1 and alpha 2, alpha 3 in a subsequent way. And eventually, if you do it successfully, you will find out the lowest element as 0 minus 1. Right? And this weight tree, this whole thing is called the weight tree. And this weight tree tells us how these epsilons and z's are connected with each other. Right? So that's what we have also noted. But now coming back to this wild character formula, there are many ways to represent these characters, but we'll work with the an expression which is basically will be useful for us. Right? Now look at the numerator and denominator. The denominator have these epsilons which are fixed for the given group, because these all the structures, these relations have nothing to do with the representations. Okay, so this is for a given group are fixed, so my denominator is basically fixed. That means whatever the representation you choose under this SUN, okay, these denominator functions will be exactly same. Okay, now the epsilons are basically my again fixed for the given group. Okay, now only way the representation dependence would come into a picture, the only one variable is R. Okay, and that's where we stopped yesterday. So now we need to learn that how R vector can be computed. So R is basically, you can think of as like a vector where you have this R1, R2, and then R0 you can define, which is basically your 1. Okay. Now this R is basically written using this vector. Now let me explain why. What is this? Yeah, up to this part, any question? You can have R basically number rank of the group. So if you want to do use R as an n-dimensional vector, one element is always 1, which is the R0, because Rn is basically 0. Okay. Okay, maybe I should put 0, not 1. Yeah. Epsilon to the power 0. Okay, so now this lambda actually has a very deep relation with the Dynkin level of the group. So this has a relation with the Dynkin level of the representations. Okay, so this lambda in the group theory, I would not go in the definition how to derive and all those things, but rather what I will tell you how you can calculate lambda for a given representations. Okay. Now, when I am saying some representations, you think about some kind of dimension, right? In the group space, we have 2 dimensions which generally talk about dimension of the group space, which is basically fixed. We have also the dimension of the representations, which also changes actually. Okay, here we are talking about the dimension of the representations. Okay, so now this dimension of the representations have a one-to-one correspondence with the Dynkin level. Okay. If I say, okay, let me take some representation R of SUN, then it will have some Dynkin level. Okay. So the question is, so what are my ingredients again? If you come by the symmetry and the representations, right? So if I need these 2 information. If I have these informations, I can construct the operators. So that is the target. So this is as an input for me. Right? I know what are the representations I am playing with. For example, if I know I am going to construct the Smith operators, so I know what are my lighter degrees of freedom. Okay. So if you do not have the information of the lighter degrees of freedom, you cannot even construct the Lagrangian. That's what you need actually. So when I know the lighter degrees of freedom, I know how they transform under the given symmetry. So I know what is the Dynkin level for that representations. Okay. So then what you can do, you can write down this Dynkin level, or maybe I can work with one less dimension. Yeah. This quantity as lambda 1 lambda n minus 1 plus lambda n. So now this weight tree components I can use as a basis. Okay, the way we use that to connect your epsilon and z. Again, this weight tree can help me to connect the lambda and the A. So you can think of the Dynkin level is basically expanded in the basis of these weight trees, okay? And each component of the basis is basically my lambda I. Okay. Just think of like the way in quantum mechanics you do, right? You'd have any vector psi which you are expanding in some ai phi I basis, okay? Your phi I, the basis is basically your spanned by this weight tree, okay? And then your psi that you are the psi that you are expanding is your Dynkin level, okay? And the coefficient of those bases are nothing but my lambda. Is that okay? Any question? Fine. So now what we can do, we can invert this relation. It's a linear relation, right? So we can easily invert this thing. Now if you invert this relation, what you can do, you can write down k minus lambda k plus 1, okay, and lambda n equal to 0, lambda n minus 1 is a n minus 1, lambda k equal to sum over I equal to 1 to n minus 1 ai minus sum over j equal to 1 to k minus 1 aj, okay, where I not equal to j. So now using this relation you can actually, now you can see for the given representations I know what is the Dynkin level, so I know all my AIs. If I know all my AIs, I plug back here and I can calculate the lambda. So this relation gives me my lambda vector. Yes, because lambda n is always 0, that's why. That's why lambda n is always 0. Because of over counting in basis I am working on. Okay. Fine. And now, what about rho? Rho is basically representation independent. So for given group SUN, rho is basically given as, it's basically rho I, where rho I is nothing but my n minus I. So let's say you start with SU3, okay? We'll do explicit example, but coming back, let's say for you are working in SU3. So what will be your row vector? The first element will be 3 minus 1, 2. Then second element will be 3 minus 2, 1. Third element will be 3 minus 3, 0. So 2, 1, 0. Now you see there is no representation dependent there as well. So now R, well, the relation So now coming back to this relation. So the representation dependent in R is coming through lambda because rho is also represented independent. And that's why the representations which is given in terms of Dynkin level is basically help you to calculate this lambda. So so just think about it. You are given this Dynkin level, from there you calculate the lambda, from the lambda you just plug in because irrespective of the representation you know what is my rho for this given group, you put it back, you get the R vector. And once you get the R vector, you basically know R1, R2, R3. Once you know them, you put in this formula and you get the character function. As simple as that. Okay? So, do you follow the logic? If you do not, please let me know. For SUN group, first of all, this formula is for only SUN. Yes. For this formula SUN, and then the methodology is basically the same, but of course, their highest weights tree and all those things are different. But exactly, that's why I'm saying that the method that I'm talking about till the calculation of the invariant polynomial will be equally applicable for all the connected compact group. So only thing basically you have to know the character function, the formula and all those things, that's all. But the method is basically the same. Okay. Fine? I have to calculate the lambda. Yes, because Dinkin level is the information that I have. I need to calculate the lambda. So that's why I have to solve for lambda. Na? Which are the? No. Lambdas, you just think of they are the basically components when you define in the vector space in terms of the weight tree. That's all. Of course, they have the mathematical meaning and all those things, but as I told you in the beginning, we will not go in the mathematical wordings. We need to know finally how to calculate the lambda. Whatever how many words we spend, right? So I am telling you how to calculate the lambda. So you, for a given representation, you cannot tell me what is my lambda, but you can tell me what is my Dinkin level, right? So from the Dinkin level, I can calculate the lambda. Of course, there's a mathematical definition there, but I am very sure the definition is not useful for me here. Exactly. Yeah. This one? Yes. So basically, you have this relation, right? So now, so you can think this is a vector, right? So component by component you match. It's like a vector equation. Okay. You just first component will match with the first component, second component, that's how. So if I write down, for example, R vector, which is basically have a R1, R2 and this thing, right? And then I have some other vector H, let's say H1 and H2. And if I demand my R equal to H vector, then I just match them and they are spanned in the same basis. Then I demand them basically to be the component wise. Okay. This is a vector equation. Yes, component wise, you just match them. That's all. Okay. There's another interesting interpretation of this lambda, which is basically from the Young diagram, because that's what you are familiar with. But I will tell you why that interpretation will not be very useful for us, but it's useful to know. For example, let's say for any SUN, you have, let's say, this kind of, let's say this is my Young diagram. Okay, I do not know what is the dimensionality, right? I get to know that, okay, for given represent, this is my Young diagram, and these lambdas are nothing but if you start from the top row, okay, count the number of boxes, okay, this is my lambda 1, lambda 2, and so on. So you start with the top box, okay, and if you calculate, then you find out the number of boxes appear in the Young diagram for that given representations is my lambda 1, the second and all those things. Now, in this way, you can justify even and argue why your lambda is equal to 0. That's very easy to understand because for SUN, okay, how many vertical boxes you can have maximum? N minus 1. You do not have n number of boxes because that's a singlet. So that's why lambda n is 0. There's no box in the nth position, right? So diagrammatically, you can also understand why my lambda n is 0. Right, so now what I'll do, I'll calculate the character for different kind of representations using this information, and the homework will be you repeat the same calculation using this Dinkin level. Is it clear? So that's how you can understand how to use them. Okay, so let's start with the simplest one, SU2. Rick, when I started? Okay, so half an hour. Okay. Okay, so now let's do some example with the SU2. So SU2, what is my rank? Rank is 1, right? So then, how many torus coordinates you would expect? 1, right? So now, epsilon 1 is basically my Z1. What will be my epsilon 2? No, epsilon 2 equal to what? Remember, epsilon is basically Z inverse. Z1 inverse. Also, the product of epsilon is 1. Remember, the product of the epsilon is 1. So, you can immediately calculate from that simply, that thing. So, now, for SU2, let me calculate the denominator first. So, that is epsilon 1 to the power 1, 1, epsilon 2 to the power 1, 1. Why? Because SU2 is 2, so n minus 1 is 1. So, you start with n minus 1, then this is 0, again n minus 1, this is 0. So, you calculate this thing. And this, if you calculate, what you find out? Z1 minus Z1 inverse. Right? The determinant. So, epsilon 1 minus epsilon 2, and that's how you calculate this thing. And what is my delta epsilon inverse? You replace epsilon by the epsilon inverse. Okay. So, what will be that quantity? Z1 inverse minus Z1. Okay. So, these are two things which are basically represent independent. I first calculate. Okay. So, now I'll calculate, I choose my first representation, which is basically my singlet. My Dynkin level is 0, and my Young diagram is this one. Agreed? Yes, we'll use that later. For the time being, I'm just calculating this thing. These two quantities I'll need later, but these two quantities why I computed earlier, because these are independent of the representations. Once I fix the group, these are automatically fixed. There is no ambiguity in this thing. Okay. Now I choose a represent singlet. So very intuitively, if I ask you what is the character of a singlet, what will be that? One, some trivial thing, and these are normalized, because that's how, if you see the orthonormality condition I'm using, right? So if it's not normalized, then it can have any number, but because I'm using a orthonormal basis for the characters, so the trivial thing could be for identity is identity, right? You don't expect, because identity is nothing, it's not invariant quantity. It should not have any information about the group and all those things. It doesn't care. So let's cross check that thing. Okay. So now, what is my lambda vector? As I told you, you are supposed to repeat this calculation using this Dynkin level information. I will use the calculation using the Young diagram. It has that you can, you can have it to calculate these things using the Dynkin level. So lambda is basically my 1, 1, because that's the count the number of boxes. Okay. Then what is my row? 1, 0, because this is fixed for SU2, right? It has nothing to do with the representations. So my R is 2, 1. So chi for singlet representations is so R1 is what? 2. So this will be 2. This will be epsilon, and then I have a delta epsilon. Okay, and if you calculate this, you'll find out this is 1. Yeah, because that was the extended object actually there. So they are actually lambda, and I'm not using that information. I'm subtracted that additional information. I mean, I can use that, but it will. I have to discard that thing. Okay. So now, let's take another example. So as you know, SU2 has a, so SU2, what are the representations? SU2? Pseudo-real representation, right? So that's why this is the equivalence we have, 2 and 2 bar. By the, I hope you know that 2 bar is not 2 star. If you are really familiar with the Dirac theory, then you must have encountered this thing, right? It's not 2 star, it's I sigma to 2 star. That's the 2 bar definition actually, right? So if you take phi 1, phi 2, you have to use I sigma to phi 1 star, phi 2 star, and that's what actually have the correct SU2 transformation, not the phi 1 star, phi 2 star. So now this is what our intuition tells, but let's check. What is the Dynkin level? Is 1. Okay. And then the Young diagram is given by a single box, because that's what the lowest dimensional fundamental representation for SUN represent. SUN n-dimensional representation is a single box in the Young diagram. Yes. That's what I'm saying. That's why his question. Because the trivial representations, okay. So either I can extend this object and put a 0 for everywhere, otherwise I can discard that thing. The special case for the trivial representations. What you are now your expectation will be similar to what for the non-trivial representations. Yes. Okay. So now let's calculate this one. So what is my lambda? In the first row I have a box 1 row. There's no box, so it's a 0. Again, what I'm saying, this writing lambda you must do not using this one but using this one, because for the higher dimension representation or SO2n or SO2n plus 1 or symplectic group, you do not know what is a Young diagram. I mean you have to really dig out mathematics book to find that out. It's better to do using the Dynkin level. Okay, so that's why I'm assigning the homework. Please repeat the whole calculation using this Dynkin level, because I have given you the prescription to do that thing. Okay, fine. So now again, my row is basically same for this group. Now R is 2, 0. Right. So now, what is my chi2? Chi2 is 1 by delta E, and then epsilon square, right? Epsilon square, epsilon 0. And remember, the relation between the epsilon and z, what I have given here, this is not altering with the representations. So that's why first, what are the group properties we have written down, okay, then we are doing this thing. So exactly same epsilon and z conversion you can put here. Okay. Now if I do this thing, what I'll find out is basically z1 plus z1 inverse. This is just calculating determinant, not even a high school algebra, so I am not doing that thing. Okay. And if you start with a 2 bar, because for 2 bar the Young diagram is exactly same, because you have n minus 1 number of vertical boxes for n bar, here it is 1, so that's why even if you start with 2 bar, you get exactly the same character. So that's why every step you can check the equivalence of the knowledge that you have regarding this representation theory. You can check with the character calculation. Okay. Yeah, any question up to this part? Fine? Good. So now, let's do the adjoint representation. So what is the adjoint representation SU2? 3-dimension representations. Dynkin level is 2. And how do you write down the Young diagram? Like this. Now, what is my lambda? Lambda is 2, 0. Rho is 1, 0. R is 3, 0. Just add them. Okay. Now, what is my chi3? Is epsilon cube, epsilon 0, and then we have a delta E. Right? Everyone agrees with this structure? Right? The first element basically your R1 and then the R2. That's all. As simple as that. Much more simpler than the integral calculus even. Now if you calculate this determinant, what you will get? Z1 square plus Z1 to the minus 2 plus 1. So this is the character function that you can calculate. Well, so now we have enough information to cross-check what we know from the representation theory again in terms of dimensionality. How? Let's see what we know from 2 cross 2 bar is 3 plus 1, right? So then if what I'm saying is true, then in terms of the character polynomial, this should be also true, right? So then let's check Z1 plus Z1 inverse times Z1 plus Z1 inverse minus 1, because that's the character for the singlet. If you calculate that, you would get Z1 square minus 2 plus 1, right? That's a nice cross check, that whatever the character function that you have computed are basically consistent in this way. Okay, minus 1 is basically the character of the singlet. Yeah, so that's why I'm taking minus. Na? So when you calculate 2 cross 2, the total polynomial has the information about the character of the 3-dimensional representation and singlet. So to get the 3-dimensional representation, you have to remove the singlet representation character. No. Character of singlet is 1. So 3, if you have to take on the left hand side the polynomial. Is that okay? Okay. Yeah, that's what we have calculated, right? 1. So now you see, the question is now, if this is again coming back to what we were discussing earlier, that in these statistics, when you take these characters and you multiply them, basically all the information about the higher dimension representation are hidden there, right? So if you take chi r twice, you get basically for the SU2 the character for the 3-dimensional representation and the singlet representations. If you multiply another, what you will find out? 2 cross 2 cross 2 is 4 plus 2 plus 2, right? So what you will find out, the SU2 quadruplet character is there, and on top of that, the 2 SU2 characters are there. So if you remove the two SU2 characters, and then if you take a cube of this quantity, you would get that thing. But instead of doing that, what we prefer to do, in this a consistent method for any given representations, we know what is the Dynkin level and we can calculate the characters. But this is a nice cross check to convince yourself that you are doing some right thing. There's no mismatch of factors and so on. So that's all, and this is so simple, right? And for the you take any SUN group now, okay, you can calculate this thing. Okay, so now I'll do one non-trivial case for SU3 and I'll give some homework. Okay. Now let's talk about the SU3. So for SU3, what is the highest weight of my lowest dimensional fundamental representations? 1, 0, right? And then what is my Dynkin diagram for SU3? 2 nodes. And then what is my Cartan matrix? 2 minus 1 minus 1 2. Right? That's my Cartan matrix. So my L1 is 1, 0. L2 is L1 minus alpha 1, which is minus 1, 1. L3 is L2 minus alpha 2, which is 0 minus 1. Right? As I told you, that will stop exactly when the last element is minus 1 for the SUN, what we have suggested, right? So that exactly we have replicated, and we have exhausted all the roots also, alpha 1, alpha 2. So SU3, the rank is 2, so that many simple root you would expect. Whatever the root you define, more than that, that will not be simple roots. They can be positive root, but not the simple one, right? So now, why do we construct this thing? Because this will help me to set up the relation between epsilon and the z. So now, using this, we have the relation epsilon 1 equal to z1, epsilon 2 equal to z1 inverse z2, epsilon 3 equal to z2 inverse. Now you see SU3 rank is 2, so I would expect how many torus coordinates? 2, and that's what we have, z1 and z2. We have removed the redundancy on the epsilon basis. Okay? Any question? Okay. And then row vector we can compute as I told you, is independent of the representations. So for SUN, there will be n minus 1, so 3 minus 1, 3 minus 2, 3 minus 3. So row vector is 2, 1, 0. So once I have the row vector and these quantities, what I can calculate my delta epsilon. That is epsilon 2, epsilon 1, epsilon 0, this determinant. And if you calculate the determinant, you would get Z1 minus Z1 inverse, Z2, Z1 minus Z1 inverse, Z2 minus Z2 inverse, and Z1 minus Z2 inverse. So this is the whole thing that I can compute even thinking about any representation of this group. So because these are the factors will repeatedly appear for my calculation of the character for any arbitrary representations. That's why my task is basically to compute them first. Okay. So now let's take a representations. Yes. Yes. Because even when you write down the field theory, for example, or particle physics model, you need to write that SU2 Higgs doublet or fermion doublet or singlet. So that information you are exactly same information you are giving, but in terms of a Dynkin level. That's all. So whatever you guys have done so far to calculate any write down Lagrangian, here we are asking any more information more than that. Those informations we are using in a different way now. Okay, because symmetry and the representation, that's what we need. Okay? Okay, any other question? Fine. So now let's check the SU3 fundamental representations. So what is my Dynkin level? 1, 0. And what is the Young diagram? Single box, because that's the for the SUN, single box. So then the lambda would be 1, 0. Right? Or if you try to extend, because here it was supposed to be one dimensional, but we have a additional over counting part. So if you want to keep the same thing, then you make lambda either up to lambda n, so you put 0 here. Okay. And then rho is your 2, 1, 0. So R is 3, 1, 0. Right? It's just a addition of the two vectors. Right. So then I can write down the S3, but these three you have to remember, this is the 3-dimensional representation of SU3, not the 3-dimensional representation of SU2. So that's why one has to be careful, and it's better initially to write down the group that you are talking about, just to distinguish that thing. So this, if you write down, you get epsilon 3, epsilon 1, epsilon 0 by delta epsilon. How these epsilons are related? This is the way all my epsilons are related in terms of Z. What is my delta epsilon? Delta epsilon is here, okay? And I know what is the expression of this thing, right? The same way we expand this thing and calculate the determinant. And if you calculate the determinant, what you will find out is Z1 plus Z2 by Z1 plus Z2 inverse. So this is my character function. Yes. Epsilon 3? No. No, it's epsilon cube. Because the power is basically your R. This R, na? Okay, so no, in this way you are writing when, is it, okay, so let me maybe, okay. So this quantity you are writing, this quantity as epsilon cube, epsilon 0, epsilon 2 cube, epsilon 2, 0. This is a shorter convention of writing. So I think, yeah, so this is the shorthand notation. If you see A star as note, this is basically your epsilon 1 R1, R2, and so the epsilon and all those things. Okay. And this is, the R is to the power actually. Okay. So now the homework is similar way you calculate the character for 3 bar. Now what do you expect 3 bar? 3 bar you would expect the exchange of Z1 and Z2, but you should check explicitly. This should be chi3 of SU3 exchange of Z1 Z2, because you are just conjugating them, and conjugate is basically inverse, right? So they are changing their positions, okay? And then you calculate the character for adjoint representations of SU3, okay? And then you cross check that this is actually chi3 times chi3 bar minus 1, because that's what you expect, right? 3 cross 3 bar is 8 plus 1 in the SU3, so that should be reflected here as well. Okay, yeah, up to this part any question? Yeah, exactly. It's a for any of these things, yes. A construction is such that it will be always like that. For SUN, for other groups where you have a half integer spins kind of thing, okay, for them you can have a root and all those things could be there. But yeah, for SUN at least all this way. No, denominator you have to calculate once for all. Factors means? Yeah, exactly. That's what I'm saying. You just write down that once for all, and then whatever the numerator you're getting, you just factor out that quantity. I mean, like taking a coset with respect to that polynomial. Any other question about the characters? Because now I move to, I think I have 7-8 minutes. Yeah, that will be sufficient to calculate the Haar measure, and that would be sufficient. But yeah, but before moving to Haar measure, regarding characters. Okay? Okay, but please do the homework. Yeah. Our organizer is here, so he will be. Okay. Okay, so now, as I told you that if you remember the yesterday's lecture, so to calculate the invariant polynomial, there are 2 parts, right? The prefixes, what we have written here, and the prefixes actually consist of these characters. So first target was to calculate the characters. Okay, now we have learned for the given representations how to calculate the characters. Second part was this one, this quantity. It is for U1 is dz by z, right? But for any general arbitrary group, what is this? That we have to find out. So if you have that idea now we can see that we can perform the residue theorem for this given character functions, okay, and we can calculate the invariant polynomial. So one component is done. Now we have to calculate the Haar measure. Okay. So Haar measure for this SUN you define as 1 by 2 pi I to the power n minus 1 n factorial, okay, and then integral, oh sorry, L equal to 1 to n minus 1 dzl by ZL epsilon delta epsilon. Okay. So now you can see that L. So this also harmonizes when you are computing the character functions are computed in the maximal torus, right? So then you have to calculate this group measure in that coordinate system. Otherwise, you cannot perform the integral, right? I mean, your measure is in Cartesian, your integral is in polar coordinate. You cannot perform the integral. So you have to translate that volume element, okay, of the group space into this maximal torus coordinates. So now, what we have done? So for SUN group, we can think of in terms of n minus 1 number of this abelian structure. Okay, so then you can think of the volume element is basically just for each unit radius circle, you take out and decompose that thing. So that's how we do this thing, dZL by ZL. Okay, for the abelian, and this is the when you go from this abelian structure to this when you embed, this is the factor will appear. Okay. So then delta of epsilon is the same delta of epsilon which is appearing in the character calculation, which you have computed, and delta of epsilon inverse, what I have defined, what did I define? Yeah. So now you can see what is the importance of delta inverse. It is nothing but epsilon each coordinates, you take the inverse. Okay, so if you know the delta epsilon, you just know by replacing all the coordinates by its inverse. So you get basically delta epsilon inverse. And once you have these two quantities, you plug in here and you get the basically integral form. And what is the counting? So all the characters are function of your for SUN n minus 1 number of coordinates, right? So that means basically you can have that many coordinates, integral over that many coordinates, right? That's why L equal to 1 to n minus 1. For SU2, you have only dz. For SU3, we have z1 and z2, two coordinates were there. So this will be like a dz1, z1, dz2, z2. So all are basically consistent. And this is just to take care about the over counting or the measure and all those quantities actually. The normalizations. Again, the normalizations we are using such that character orthonormality condition is satisfied. So in this way, if you define, then you can check for the SU2, my delta epsilon is Z1 minus Z1 inverse, and then delta epsilon inverse is Z1 inverse minus Z1. So the product of delta epsilon times delta epsilon inverse is 1 minus Z1 square, 1 minus. Okay. So how do you write down the then d mu? This 1 by 2 factorial dz1 by z1, and then you have this quantity. Okay. So if you then d mu of SU2 is 1 by twice by I 2 factorial dz1 by z1, and then delta epsilon inverse. Right? And if you want to do for SU3, what will be that? So d mu SU3, that will be 2 pi I whole square 3 factorial dz1 by z1 dz2 by z2 and delta epsilon and delta epsilon inverse, but this is for SU3, right? And this you check that this quantity is actually 1 by 6 times 2 pi I whole square dz1 by z1, dz2 by z2, 1 minus z1 z2, 1 minus 1 by z1 z2, 1 minus z1 by z2 square, 1 minus z2 square by z1, 1 minus z2 by z1 square, 1 minus z1 square by z2. Okay. So just we have a delta epsilon by this definition. You can calculate the delta epsilon inverse by changing the inverse. You just multiply and you should get this answer. So now for the standard model, what are the internal groups we have? SU3, SU2, U1. Okay, and what are the representations? SU2 doublet, singlet, SU3 triplet, okay, 3 bar representations, conjugate representations, right? And you have an adjoint, and SU2 also you have adjoint. Now you see, we are ready to write down the character for all the standard model fields that we will be dealing with. So the internal symmetry and their characters and their Haar measures we have taken care of now. Okay. So what will be the next task? Take care about the space-time symmetry, because we have a fermions and field tensor which transform non-trivial under the spins. Okay. That, and also the covariant derivative which also singlet under the internal symmetry, right? But it has a non-trivial transformation as a bispinner under the space-time symmetry in 3+1 dimension. So we have to know how we can write down their representations in terms of this character function. And then along with that, we have to be also careful, because we don't want to create only the group union polynomial, but we also try to remove the redundancy due to the equation of motions and the integration by parts and all those things. Okay, so that will be the next target. But before doing that, next time I'll discuss basically for this individual group I have mentioned. Okay, so now if a product of group, okay, and the multiple representations, how do you generalize the placistics for the scalar and the fermion? So far we have done for the scalar. There's one slight change in the fermion case, and that will be done for us. Okay, yeah, I think it's a good time to stop. Yeah. So there's a theorem which says that this method can generate all the required terms. You can prove actually. For like any general representation. Yeah, as long as basically, as long as you are work in a connected compact group, this works. And if there's a proof. Yeah. Odd rank means basically? Okay, for SU when you are talking about? Okay.